All right. So today I will start talking about formal quantum mechanics. Use a different color. So we have plenty of motivation to think about non-classically, right? We have de Broglie, we have like particle-wave duality, we have all those things. But now we are adults, we can do things the proper way. And we are not going to just like draw waves and fit things inside and outside. We are going to be a little bit more consistent. And we are going to think about wave function. So let me remind you what we mean when we say wave function. So if you remember, we introduced, we said like matter also like has like a wave property, and when we asked like what is waving, we said wave function is waving. It's not an observable, but we said like it is like a unobservable aspect of nature, and we said it is like a function of x, y, z, and t, and it is complex valued. So this is what we call wave function. So this thing, so it is complex, and what complex means is it has like real and imaginary parts. So this is like something like u, a function of x, y, z, and t, plus I times v, another function, x, y, z, and t. And here this I was equal to minus square root of minus 1. So since this is like a complex quantity, it is not observable. And it took a while to make a sense of this object. And we mentioned the proper way we utilize today is like so-called Born interpretation. So in this interpretation, psi is probability amplitude. So what is probability amplitude? Probability amplitude is the object. When you square, it's going to be the probability. So if you want probability to observe particle at x, y, z at time t. Good? And once you, we have to have a way to obtain psi. At the moment, we don't know how to obtain this. But once you obtain psi, you basically solve all problems. Everything you need, every observable can be obtained from psi, which we'll see today in detail. So what does complex means? So let's think about complex numbers a little bit. So if psi is equal to this u plus iv, I want to introduce complex conjugate, and the notation is like this. Psi, you put like a star next to the complex number, and it is defined, so this is the definition. Wherever you see I, you just put minus I. That's the definition of complex conjugate. So this is u, I, v. Because u and v were real, there was nothing to do about it. The only thing is this like imaginary unit. So I want to introduce something called, so this is the complex conjugate. And I want to introduce norm. Norm is u multiply psi with this complex conjugate. So let's do this. This is u minus iv, u plus iv. And this is equal to, so this is u square plus I uv minus I vu. So minus I times I is minus I squared, but minus I squared is minus minus 1, which is going to be plus. So this is going to be v squared. And as you can see, so this thing is going to cancel this, and at the end you are going to put u squared plus v squared. That's the norm. So how many people know this? Okay, good. Plenty of people know. So when you see u, you don't have to open this up and do this multiplication every time. You take the first amplitude, square it, take the second amplitude, this v, and then square it.
So physically, what's the meaning of norm?
So the norm is like this, psi squared, and according to Born interpretation, it is the probability. Probability to find the particle at x, y, z, and at t. So that's our if you want, postulate. There's no proof of that. Like, we have to come up with a set of postulates which has been tested over time, and we know today they are working. So we have to understand the postulates, and we have to know how to use those postulates. And one of the most important postulates is the norm is the probability. Yes.
Shouldn't we apply the operator to find the probability of finding this value at
Yes, so we will come to that. Yes, so we in a little bit. So this is we start the step number 1. We have to give a meaning to psi, and now once we understand psi, we are going to introduce so-called operators, and those operators, when they do the right thing to psi, they are going to give us the observables. But for the probability which is observable, we don't need any operator. Psi itself is sufficient to get the probability. But that's a good point. Since psi is a probability, and we know from the probability that if you sum everything up, you better have 1, right? If you sum all the probabilities, you have 100%, and we are in the probability, we are writing things in terms of unity. So 1 means 100%. Then we need 1 is equal to. Let me consider only one dimension, so we can write more if you want. We can. Let me actually write it into dx, dy, dz. This is summation over all possible x, y, and z. And if I do this, x, y, and z, this should be 1. So this is what we call normalization. Good. Simple stuff. So there are other requirements. So other technical requirements.
So can you explain that one?
This one?
Yeah.
So because we said this object, we said it is probability, and if it is probability, and if you sum over all possible events, right, that's by definition everything, and everything is 1, right? Yes. So this is x minus infinity to plus infinity, y minus infinity to plus infinity, and z plus minus. Basically, you are integrating all universe. If you sum everything possible, you had the 100% probability. Good. So if psi is probability, you better have psi should be nice in that sense. Psi should be single valued. I mean, if you have in mathematics, we know there are multi-valued functions, right? If for a given x, y, z, t, you have multiple psi's, that's nonsense, right? You have to be able to pick the value, so it has to be single valued, and it has to be continuous, which is a physically sensible thing to ask for. I think it's not too much. The second, the derivative of psi, let me call it psi prime. This prime could be derivative with respect to x, y, or z. Also should be single valued and continuous. And lastly, psi should be, let me like make up this word, should be normalizable. So what this means is when you take the square like this, you better have like a finite value. If this integral blows up, right, you have like nonsense. This is sometimes what people call square integrability, right? If you take the square and integrate, you have 1, that means it's like square integrable or like normalizable. And for this to happen, you need to have psi, right? Psi should go to 0 as x, y, or z goes to plus or minus infinity, right? As you go to plus or minus infinity, if you are not going to 0, that means you are adding up more and more and more stuff. This more and more and more stuff should going to blow up otherwise. Any questions?
What did you mean by single value?
Like single valued, like we are drawing functions, right? Here is the function. This is f. Let me call like f of x as a function of x. Single valued for every x, you need to have one f, right? Something like that. For example, this one is not single valued, right? If I have something like that, and at a given x, for example, am I supposed to pick this one, or this one? I don't know which one to pick. So then I'd say that this is nonsense. I mean, mathematically fine, but we cannot use it for...
That was the property of a function.
Yes, yeah, right? So this is not single valued function, whereas something like this is single valued, right? There's only, for a given x, there's only one value of f. It's like the dictionary definition of single valuedness. Good?
Vectors also have true value, right? I mean, the wave function does not be a vector. It's also
Even if it is vector, right, it can like have multiple components. At some point we are going to come to that. Even if it has multiple components, it has to be unique, right? Like, yeah, say you have like x1, x2, x3. There will be complicated wave functions like this. But this, I don't know, let me call this like a vector, should be single valued, because if you put inside the psi, and if you have like two different, like, right, at the end, you are going to give whatever you want to give to psi, and it's going to spit out a number. That's the definition of function. Function, whatever you give to it, is going to give you a complex number. And if you give the same thing but get two different results, that's nonsense. The single valuedness does not necessitate scalar input. You can have a vector input and still require single valuedness. Does that make sense? If you didn't understand that, forget that. I think for the moment we don't need complications. So then here's the important bit. So psi is a wave function. Then we need something, right? For waves, how do we study waves? Before, like, usually, like in classical physics, we don't start with wave function without saying anything about it, right? We need a more firmer ground to start with. What is the reasonable requirement for us to determine psi, right? If we are talking about waves, we need a mathematical object.
Amplitude?
Like amplitude is this going to be, like we are solving things, right? What do we need? Equation, right? What kind of equation? Huh? Wave equation, yes. So this is like psi is like a wave function, so we need a wave equation. Like for example, like waves in a string, they have like a wave equation. Light comes from Maxwell equations, which is possible to, as I showed you before, is like a wave equation. My sound coming to you is coming through like a wave equation. Waves in a vibrating spring is obtained by like a wave equation. So if we are talking about waves, we better write down a wave equation. And let me first write a wave equation that we know how to deal with. So this is del f, del x squared minus 1 over v squared del f del t squared is equal to 0. So this is usual ordinary wave equation. And it would actually be nice to be able to just put here psi and solve this and say, oh, this is our wave equation, but it turns out not to be the case. We'll come to that in a little bit. So this is f. So this is f. Yeah.
It's not a mathematical question, but why do we need the del operator of the time?
Because this is like the ordinary wave equation, right? Wave equation means what? As a function of position and as a function of time, you are waving, right? You are propagating in time and space, but you are propagating in like a sinusoidal wave, right? And this sinusoidal movement is described with this kind of wave, right? Like you have to have like both change in x and change in t, right? So if you have never seen this, that's fine. I mean, this is like
Yes, it's very
near to you, right? Okay, that's fine. Then like this is a wave equation, and it's possible to solve this. I'll actually tell you a little bit about how to solve this, and then we'll come to psi in a little bit. So here is like a little exercise for you. Exercise. Any function, take your favorite function and substitute x plus or minus vt into here, and this is solution of wave equation. So this is like a simple exercise. You just need to like exercise these partial derivatives. So this one means by the way, so this is partial derivative. So what this means is like hold everything else fixed, like, and take a derivative with respect to x, right? So your function f can be x, y, and z. And if you are taking partial derivative with respect to x, you are like pretending y and z to be fixed and taking a derivative with respect to x. So that's the definition of partial derivative with respect to x. Same for y and same for z and same for t, if we have t here. And this exercise, I tell you, is like simple exercise of these partial derivatives. If you have never seen partial derivative, sit down and do this. It's like a 2-minute exercise. And the solution, like there are like special solutions of this. Like I said, any function of this form is solution, but there are like special solutions which we call plane waves. They are going to be very handy for us to solve problems, and they have the following form. Some constant a times e to the minus I omega t minus 1 over vx. So if you substitute, okay, this is also exercise number 2. Substitute this and show that this actually satisfies the solution. Okay. Now, our goal is to obtain a wave equation for psi, right? So let's take this solution. Let's say, okay, we have already seen like quantum mechanics and classical mechanics, they should agree, right? Like at some point. And we can think about this classical wave and just like say, let's try this and see what gives us. Let's say my psi of x comma t. Let's not make it complicated. I am going to drop y and z components, and we are only going to look at a one-dimensional wave. So let's say my wave is given by this, e to the minus I omega t plus I omega over v x. And from Planck, okay, let's use what we know in quantum mechanics. From Planck, we know energy is h nu, and we can write it like h power omega. And this says omega is going to be 2 pi nu. And for v, you can think about like speed of light, right? It is like the wavelength times frequency, but we are not like looking at like a wave that propagates with the speed of light. We are looking at like another kind of wave, so let's make it v. So that is the relation. Then this psi object, psi of x comma t, can be written as a times e to the minus I 2 pi nu plus, and for 1 over v, I am going to write this identity, and it is going to be I 2 pi over lambda times x.
Where is t?
So at the moment there is, okay, I think where is t? I think I am sloppy. I think it should be here, right? This one. Thank you. I think that's it. Did I get it right? So this is a minus I omega. This is plus, yeah. I think it's right now. And also, I remind you, de Broglie momentum is equal to h over lambda. And if I, like energy is h nu. So let me use those. So this one, so I can do the following. So this is, I can write E divided by H, right? And for this, for the second one, I can write P. Okay, let me do it one more time. So I can multiply and divide H, and H over lambda is P, so this is P. Let me clean that up. So this is A e to the minus I over h bar, right? Now this is h over 2 pi. I put h bar e times t plus I p over h bar x. Okay, so far we didn't do anything. We just rewrote the wave that we know should work out. And now I look at psi and I ask, how can I obtain the observables I need from this psi, right? And the way I think about this is like, okay, I look at this and I can already see if I, for example, take the derivative with respect to time. Let's see what this gives. Del over del t, psi of x comma t is going to give me, right, only this part, minus I over h bar times e and psi itself. Is it clear? And then if I say like I multiply both sides with I, like this is gone. I multiply both sides with h bar, so this is gone. So it seems like this object gives me the energy. So this seems to be identified with this, right? Is that clear?
An operator can be.
Exactly, right? Like I am like the operator is what? Operator is giving me what I want. That's the definition of operator, right? And I operate the object, and it spits out what I want. At the moment, if I want energy, this object, operator means you have to act on something with it. By itself, it's meaningless, but when you act on it, when you act with it on a wave function, it gives you something sensible. Good. It's a little bit like a terminology, but I think my experience, people like that stuff because it's like easy to like operate, right? You just take derivatives and it gives you the energy. Similarly, I can consider, if t is doing that, let's also consider x. So del x, psi of x is going to now, okay, I'm going to act on this side, right? And it's going to give I p over h bar times psi itself. Then similarly, I can say, okay, multiply with minus I and take this one, multiply with h bar, take this one, and this is psi of x. Oops. Let me take this one, and this is psi of x. Then, so this object is going to be identified with this thing. Any questions or comments? I took it on the other side, right? It is like minus I h bar del x gave me p. I think this is the correct form, I remember, but you can do it for yourself and see. People generally have like this I factor mixed up, so it's good that you are careful, but yeah. Every time you have a problem, you can go back to here and take the derivative, and it's going to give you the result. Yes?
Wave function is time dependent. I shouldn't be finding it.
No, you should be, right? Like wave packet does not say anything about it. Wave packet is like a wave, like it depends on both x and t. Oh, yes, I see. So this is slopiness. I apologize, you are right. So I can similarly say like, okay, let me, for example, calculate kinetic energy, and it's going to be an operator acting on psi of x comma t, and from here I can tell it is going to be like, right? Let me use my classical knowledge. Kinetic energy is 1/2 mv squared, which can be written as p squared over 2m, and it is going to hit on psi x comma t, and if you do that, right, it is going to be, for example, let's do that. Now I know this prescription, p is going to be minus I h bar del x, then this is going to be minus h bar squared over 2m del x squared psi of x comma t. And for a free particle, I only have kinetic energy, right? There is nothing else. Then E should be is equal to p squared over time. Okay. Free particle means what? Free particle means E is equal to p squared over 2m. Then if I come back to here, how do I obtain E? I obtain E by hitting with I h bar del t psi of x comma t. And how I obtain p squared over 2m? By multiplying with this h bar squared over 2m del x squared psi of x comma t. And this is your Schrodinger equation for a free particle. Is that clear? Any problems? So this was for free particle. Then, okay, I think we have the pattern, right? For a particle in a potential, which may or may not depend on time, but let's keep it general, right? We know from classical physics, we add the potential and we have the total energy, right? Kinetic energy plus potential energy is total energy. Then I can use that information and modify this thing. And how do I modify it? I'll just take this and add my u of x comma t and hit on it with this entire thing. And this is what we call Schrodinger Schrodinger equation. Okay, this is the most important equation we have written so far, and I expect you to memorize this.
So we added total energy, but times, is it multiplied by psi?
Yes, like this inside, so this object, right, this entire object is multiplying psi on the right hand side, and on the left hand side this object is multiplying psi. Because this we showed is going to give you the E, and this first one is going to give you p squared over 2m, and to get the potential I add u.
But that's just an operator.
Yes, everything is operator here. So this is like an operator identity that should hold for you to have this matter wave.
Yeah, but we need to, for example, del square over del x square, we need something to operate, right?
Yes, you are operating on psi here. Right, there is psi. This entire thing is going to move to the right and operate.
So u times psi.
Yes, yes, yes. Normally we have E is equal to p squared over 2m plus u. In quantum mechanics, we promote these observables to operators, and we hit on wave function with these operators. Good. So this is what we call Schrodinger equation. Like I said, if you work by memorization, that's fine. And I sometimes see like third and fourth year students not able to write this. And I think it is completely unacceptable. If somebody asks you and you cannot write this, I think you shouldn't be here, unfortunately. Right? If you are like shaking your hands and like doing this, this is not optional. If you are a physicist, I think I expect everyone, at least in the second year, to get this straight. So let me, also maybe I can ask you like, so this is, okay, a couple of notes. So this is not a proof. So this is not a proof. And nobody can prove it, right? So if you ask me to prove it, I can, for example, ask you to prove Newton's equations, F is equal to ma. How many people can prove F is equal to ma? How many people can prove it? Nobody?
It's like a postulate.
Exactly, nobody can prove it. There is no proof. How many people can prove Coulomb's law? Can you prove Coulomb's law? How many people can prove, like, for example, speed of light is constant in all frames? How many people can prove this? Nobody can prove these things. Unfortunately, this is how we do physics. If you are asking for proofs, I think you should go to the next building. So here, we write things, and we look at nature. If it works, we say, oh, that must be truth. And this Schrodinger equation has been tested in like countless experiments, and today nobody has any doubt that it is true. Yes? It is a wave equation. Right?
It's missing the del over del t.
Exactly. Right? That's the quantum mechanical wave. Unfortunately, it's not, right? There is del over del t, but it's the first derivative. Whereas in the classical waves, we had second derivative. And there is a story behind this. Schrodinger actually tried the second derivative when he was trying to come up with a wave equation. For some technical reasons, it doesn't work. Actually, not very deep. If you write a second order wave equation and look at the probabilities do not come out to be positive. So you can show it like a wave, a function that obeys a second order derivative. If you look at the probabilities, there's something called like a continuity equation. It's a little bit calculation, which you'll, by the way, see next year in quantum mechanics 1. So it doesn't give you positive definite probabilities, psi squared. So it has some unwanted object. That's why Schrodinger abandoned second derivative, and he came up with this. And this one seems to satisfy all requirements.
So it is wave.
It's a wave equation, and it is first order in time. Any questions or comments?
So we cannot prove it because it's not kind of a definition?
We
Is that good mathematically?
no, we just like this is what we outline is just a motivation, right? Like I could like come here and write you this, and I say this is Schrodinger equation, this is what we are solving, and it would be fine. But like
Defining dot product in there.
dot product.
I'm defining, so
Uh-huh.
proving dot product is meaningless. So proving this thing
Uh-huh.
is also meaningless. Same.
Oh, I see. Yes, yes, yeah. There is no. I mean, of course, people may ask for proofs, especially if you are mathematically inclined. But more often than not, we don't care about proofs. At least physicists. I think this is a nice thing about physics. Whether you can prove it or not, it's not our concern. But I think mathematicians, they are trying to make a mathematically sensible quantum mechanical theory, and it's, I think, still an open problem today. So it is like, I'm not saying it is like something in vain. People are working on hard for, I think the quantum mechanics we use today was formulated in a mathematical framework by von Neumann, and he had some like loopholes, and they were later like fixed. But like even in this form, it requires like a mathematical foundation, which is not our job, in my opinion. Right? Mathematicians, they can do that. We are going to do other things.
So what's the scale of this function?
Scale?
I mean, for example, can we use this function in the classical mechanics problem?
So this function is, I think, as far as we know, is the most fundamental equation in nature, right? If you want, this is the theory of everything, right? Like by starting from Schrodinger equation, you can derive Newton's equation, for example, and you are going to do that. It's not very technical. It's like very easy proof and theorem. But from this function, you can, for example, formulate, I don't know, nucleus. You can formulate fundamental particles. From this function, we are going to see we can like describe atom to like an incredible precision. Like every experiment done in every lab is described by this function. In principle, chemistry comes from this function, and then biology comes from this function. Entire universe, in principle, comes from this function. But the problem is, you'll see, in general, you cannot solve it. Even you are going to see, like for like ultra simplified problems like hydrogen atom, the solution is like horribly technical, and once you go beyond hydrogen, like for helium, in 2024, nobody can solve it. So this is the theory of everything, but it is unsolvable. Okay?
You said it's like F equals MA that they saw it works in lab, right?
F is equal to ma works in lab, yes.
So you said this one works as they observed in lab.
Yeah, you can derive F is equal to ma, Newton's second, from.
No, I'm not asking about that. I want to know how they observe this works. Like, can you tell us about the story?
So, okay, this is not like, here is a little, for example, how do we know Bohr model is correct, right? Bohr model is correct because it first satisfies the spectra, right? All these like Lyman series, Balmer series, Paschen series, all of them comes from Bohr model. So this can't be accident. Second, Franker's experiment shows exactly what Bohr model suggests. But there are other technical aspects of spectra. For example, some spectra, you have to count the spectral lines, and there are additional lines that doesn't satisfy the Bohr model. Right? This is one thing. For example, hydrogen atom. If you want to describe this in full detail, you cannot do it with Bohr model. And if you want to look, for example, like other properties of orbitals, which we'll come to, like angular momentum and all the spin, like so-called Zeeman effect, anomalous Zeeman effect, we have like a catalog of experimental results, and you cannot explain them with Bohr model. But if you solve the Schrodinger equation, you explain almost all of them, right? And that's why Schrodinger came up with this, and when he just solved, I think he first solved this for some toy problems. He solved it for like harmonic oscillator, which we are going to see. And then he solved the hydrogenic atom. When people saw that, people had no doubt that was true, because it can't be accident that you are fitting so much data with one equation. Any comments? Maybe we can take like a 10-minute break, and when you come up, we can come back, we can continue.